We are going to talk about exponential tail bounds today. So we're going to find upper bounds on the probability of rare events. So here's the outline for our talk. So first we're going to introduce some preliminaries, like probability, what random variable is, what independence is, etc. Then we're going to derive tail bounds for a Gaussian random variable and expand further into more general families, such as subgaussian family and the subexponential family of random variables. And we will derive tail bounds for all of them. So to start things off, let's consider this semi-fun, motivating example. So when the euro was just introduced in Europe, these two statistics teachers in Poland asked their students to spin their coin 250 times and they obtained 140 heads. So they claimed that this means that the coin is not fair because we expect 125 times if it was fair. So we can ask ourselves a question, well, are they correct? So how likely is it to happen that the coin gives 140 heads, or perhaps 140 or more heads, if it were fair? So mathematically, we have a random variable from binomial, and we can ask for a bound on the probability that you see here. So as far as I understand, we cannot use the central limit theorem here, at least not immediately, because we have the Berry-Essen theorem, which gives the rate of convergence for the CLT to the normal. And this rate of convergence is too slow. So the rate of convergence is something like 1/√n, where n is the number of samples, and we want something exponential. So it's just not going to work here, at least as far as I understand. But we're still going to be able to deal with this example. Okay, so first, let's just introduce some preliminary stuff. So, okay, we have a probability space, which is just a measure space with total measure 1. We have probability on this space, which is the measure. Measurable functions are random variables. And we can measure probability in R or in omega. So for any random variable, we have a cumulative distribution function, which is defined in the standard way, such that it's left continuous. And we're going to sort of need two special families of random variables, the absolutely continuous ones and the discrete ones. So the strict definitions are here, but what matters is the intuition, right? That for the absolutely continuous random variable, the cumulative distribution function is sort of continuous. And for the discrete, it's just a pure jump function. Okay. So hopefully all of these are familiar, and the expectation of random variable is just the standard definition. And specifically, if we're talking about an absolutely continuous or discrete random variable, then we can specialize the definition of the expectation to the respective definitions that you can see here. So in this talk, we're going to use the moment generating function very heavily. So let's just recall what it is. It's simply the expectation of e to the power of lambda x, where lambda is the argument that the moment generating function takes. And it's almost like the Fourier transform of the probability density function of the random variable. And just the reason it's called a moment generating function is because it does generate moments, specifically the kth derivative of the MGF. So I will be saying MGF instead of moment generating function. So the kth derivative of MGF at 0 gives the kth moment of x, which is expectation of x to the k. Okay, So we're also going to be using mutual independence in this talk. Specifically, we'll need mutual independence to derive stronger, specifically exponential bounds. Otherwise, we cannot. So the definition is sort of standard, that the CDF of the joint CDF is simply the product of the individual CDFs. And it mirrors the definition of mutual independence or just independence of sets, right? So for just two sets, they're independent if probability of A and B is equal to probability of A times probability of B. Okay, so let's move on to the actual content of the talk. So the very first basic inequality that we're going to use a lot here is the Markov inequality. So here's the statement: for a non-negative random variable, it's important that it's not negative, and t bigger than 0, we can bound the probability that x is bigger than t by the expectation of x divided by t. Right, so you can see that this bound is sort of not, well, it's definitely not exponential in anything. And it decreases as 1 over t. So it is important to note that without any additional assumption, this is the best inequality we can hope for, at least for non-negative random variables. So it is tight. There are random variables for which this inequality is actually inequality and equality. So let's just look at the proof of this. It's very short and it's kind of nice because it's very probabilistic. So we're going to define an indicator random variable for the event x bigger or equal than t. And we're going to note that t times this indicator random variable is less than or equal than x, right? So if x is bigger or equal than t, then this I is 1. And so on the left-hand side, we have t, but x is bigger than t by assumption. And so if x is less than t, then I is 0, right? But x is not negative. So again, it's bigger than t times I. And so since t times I is less than x, their expectation follow the same inequality. And by the linearity of expectation, we can pull the t out, and expectation of I is simply the probability of the event x bigger or equal than t. So here we have our proof. Very, very nice. Doesn't use any assumptions about x, except that it's non-negative. Okay, so we are going to improve on this bound, and we are going to get something exponentially decreasing in t. But for that, we're going to add some assumptions because, like I said, this is tight for general random variables. Okay, but before we try and talk about mutual independent random variables, let's obtain a very special tail bound on a very special random variable, namely the Gaussian random variable. So just to recall, a Gaussian random variable with mean mu and variance sigma squared is given by this probability density function that you can see here. So you can see that for mu equals 0 and sigma equal 1, it specializes to simply e to the power of -1/2 x squared. Okay, so you can already sort of see that it's exponentially decaying in x, right? So as x getting bigger, so further from the mean 0 or mu, the PDF is getting exponentially small. So that's already a hint, right? So today we're not only going to use the binomial distribution as our motivating example, but we're going to aim for something slightly more complicated, namely the chi-square distribution, which is simply the sum of squares of Gaussian random variables with mean 0 and variance 1. So we're going to obtain, or at least, well, yeah, we are going to obtain a probability bound or a tail bound that is exponential in t. So you can see here, this is the form that it's going to take. So we're going to normalize our random variable. Oh, and it should be, I guess, parentheses here that I forgot. So the probability that it's further from the mean by t is going to be something exponentially small in t. Okay. So, and here's a picture from the standard stats class. Okay. So let's just, I guess, recall the moment generating function for a Gaussian random variable, because we are going to use it in our first tailbound. So the important thing to remember is if mu is equal to 0, then the MGF is given by e to the power of lambda squared, sigma squared over 2. Right? And if sigma is 1, then it's just e to the power of lambda squared over 2, where lambda again is the argument that the MGF takes. So we're not going to go over the proof. It's just very direct computation of the integral. Nothing tricky here. But we are going to use this MGF now. And before we do that, we're going to make the most important observation that we will use in all our future tailbounds in this talk. So namely, we will apply the Markov inequality to the moment generating function. So specifically, we have that for any lambda bigger than 0 and absolutely any random variable x, we have this chain of, well, inequality and an equality and then an inequality. So first the equality. So the probability that x is bigger or equal than t is the same as the probability that e to the power of lambda x is bigger or equal than e to the power of lambda t. Why is that? It's because e to the power of lambda times an argument is an increasing function, right? So if you exponentiate, then it's an increasing function, so the event is the same. And now this inequality is just Markov inequality, right? Where the thing in red is the MGF. So we can already see that we get something that is exponentially small in t if only we can bound the MGF nicely. So indeed, we can do it for a Gaussian random variable. It's very straightforward. Since we already know what this is equal to, right? This MGF is simply e to the power of lambda squared over 2, at least for mu 0 and sigma 1. And so just by direct computation, by plugging in our MGF formula, we get this very nice bound for the probability that x bigger or equal than t. And it's exponentially small in t, even t squared, which is better. So I guess better for t bigger than 1. So the proof is simply applying fact. Okay, so let's move further. Let's define a subgaussian random variable, which is a more general family of random variables. So, well, going back here, given any random variable, if we can bound its MGF, we can obtain a similar tailbound. So that exactly motivates the definition. So a random variable with some mean mu that is finite, right? Is subgaussian with parameter sigma if its MGF is bounded by the MGF of the Gaussian random variable with variance sigma. So mathematically, we have this inequality here. So the bigger the sigma, right, the bigger the variance of the corresponding Gaussian random variable, the sort of intuitively the worse or the looser our bounds will get, right? Because bigger variance means events that are further from 0 happen more frequently. Okay. So it's a pretty straightforward generalization of the Gaussian random variable. Let's just do an example. to sort of get our hands a bit dirty. So we will show that the Bernoulli random variable is subgaussian with parameter 0.5, and it is tight, so you cannot get it better than 0.5. So it's just pretty straightforward computation, which basically just involves the Taylor expansion of this function. So we will see that this is just one special case of Hoeffding's lemma that we'll encounter soon enough. Okay, but for now we have an example of something that is subgaussian. So let's derive a tail-bound for a subgaussian random variable now, which is very similar to our previous tail-bound. So since all it takes is to bound the MGF, by this fact, all it takes is to bound this MGF to get a nice tail-bound. And in the definition of a subgaussian random variable, we already bound the MGF. We basically just have it, right? So this is just writing what we've said already mathematically, right? So here's the MGF that we aim to bound, and we do bound it by the MGF of the corresponding Gaussian random variable, right? So here you can see the sigma, which is the variance of the corresponding Gaussian random variable, and we already have a nice bound on Gaussian random variables. Okay, so it's really basically the same thing. Okay. So now it is important to realize that this definition is not so straightforward to check. It is unclear, or at least I don't have good intuition for, which random variables follow this inequality and which don't. But we do have a very general, or a rather general family of subgaussian random variables. So namely all almost surely bounded random variables, which is, quite good. And the lemma also gives us the corresponding variance, which is the length of the range over 2. So by itself, this lemma is not that insightful because, well, bounded random variables already have sort of nice tail-bound properties, specifically the probability of x being bigger than b or less than a is 0, right? That's what it means to be bounded. But we are going to use this further, specifically talking about binomial, for example, because Bernoulli random variable is bounded and a binomial is just a sum of Bernoullis. Okay, so here we have a sketch of a proof. So we're not going to go over the full proof because it's long and not too insightful. It is insightful, I guess, if one wants to get a refresher on like calculus. So we just use convexity of the exponential function to get this inequality, and then well, use some trickery to show that actually this thing on the right is e to the power of some function of h, where h is well, cleverly chosen. We then use Taylor expansion and for L and obtain the bound. Okay. So the important part is the actual result. So let's show what happens if we add two independent subgaussian random variables. So what will happen is that the sum stays subgaussian, and the parameter is this, right, where sigma 1 is the variance of the corresponding Gaussian random variable for the first subgaussian, and sigma 2 is for the second subgaussian. So it's just direct computation where we use dependence and subgaussianity, right? Nothing over here. of course, it extends to an arbitrary finite family of mutually independent subgaussians, simply by induction. Right? We do need mutual independence here, not just independence, not just pairwise independence. Okay, so here we get to our first actual interesting tail bound. So if we have a set of mutually independent subgaussians, when we take their sum, well, it stays subgaussian, like we already proved. And we already have a bound on subgaussian random variables. So here, by what we already said, we have a nice bound on a sum mutually independent subgaussians, which looks exponential in T, which is exactly what we wanted. And of course, so M is the sum of squares of the corresponding variances. And of course, as the variances get bigger, the bound gets worse, right? So if M here is large, then this bound is not great. Okay. But the important part for now is that it is exponentially decreasing in T. So now we can return to our motivating example from the very beginning and simply apply what we have before. So a binomial is the sum of Bernoulli random variables. And well, so the Bernoullis are subgaussian. So we can just straightforwardly apply what we had on the previous slide to obtain a bound like this, right? So with our European coin, T was 15, right? And N was 215, I think. Yeah. And so if we plug in the numbers, we see we would see the actual result. Okay. And here's a nice picture of what is happening. Okay. Unfortunately, this approach will not work for chi-squared distribution, which was our other motivating example. So it turns out that chi-squared, or rather the square of a normal or a Gaussian random variable, is actually not subgaussian. So here's just some calculation that shows us that the MGF of z squared, so z is the Gaussian random variable, the MGF of z squared is indeed bounded by the MGF of a Gaussian, but only in some interval for lambda around 0, right? So so MGF is a function that takes in lambda, and sort of the important part is around 0. So that follows from the fact that the kth derivative of the moment ranging function at 0 gives you the kth moment for the random variable. So really, what all we care about is some interval around 0, and this intuition we will see that it does work, and we will get a nice tail bound for a subexponential random variable. Okay, but for now, we just note that z squared is not subgaussian. Okay, but it is subexponential. So the definition of a subexponential random variable is almost identical to the subgaussian, except we now have this interval. So we say that a random variable is subexponential if the same thing the same bound is holds. So its MGF is bounded by the MGF of a Gaussian random variable with variance sigma in some interval. So clearly this is a generalization of our previous family. So even though a subexponential random variable's MGF is only bounded in some interval, we'll still have a nice tail bound. So specifically, we have the following theorem. So we're only going to consider the upper tail bound, right? But the lower tail bound is going to be symmetric. So, okay, we do the same thing as before. We center the random variable. We ask for the probability that it is bigger or equal than some t. And we do indeed obtain a nice exponential tail bound. Unfortunately, now we can't have one tail bound for both cases, because now we sort of have this dichotomy where, not dichotomy, but we have like two cases where either we are within this interval or outside or not. And so this is the reason for these two cases. So let's just go over the proof, which is very similar to the proof we did before. So if t is less than or equal than sigma squared over alpha, and well, the exact form here that it's sigma squared over alpha is not that important, but if t is small enough, then we are, so we can let lambda equal t, and the proof is the same exact proof as we had before. So the new part is when t is large, so when t is bigger than sigma squared over alpha. So well, we still have the same fact, the same most important fact that we've been using this whole time, and we want to bound this quantity, right? This MGF, and we still can. Not by letting t equal alpha, but by, or not by letting lambda, sorry, not by letting lambda equal t, but by letting lambda equal 1 over alpha. So we still have something exponential in t, but now here we get the alpha term, but it looks almost the same. Okay. We, as you might guess, we still have the same result that if we add two independent sub-exponentials, so this is wrong, it should say sub-exponential, I apologize. We get a sub-exponential random variable back. And this parameter is, well, the same as we saw with subgaussians. And this is just, we have two intervals, one bigger, one smaller, and we select the smaller one by selecting the bigger of the two alphas, because the intervals are given by 1 over alpha. So this actually mimics the same result for just a Gaussian random variable, because if you add two independent Gaussian random variables, their means add and their variances add, well, not quite. So the new variance squared is the sum of all variances, sum of squares of all variances. Okay. The proof is the same as for subgaussian random variables, the sum of subgaussian random variables. So not terribly insightful. And of course, we have the same result where it extends to an arbitrary finite family of mutually independent subexponentials. Okay. So as you can see, we use the same exact techniques for subexponential random variables as for subgaussian random variables, except we have this interval that we now take care of. And now we can actually deal with pi squared, the squares, the sum of squares of Gaussian random variables. Because as we saw before in our example here, a square of a Gaussian random variable is subexponential with these parameters. So the corresponding variance is 2, and the interval is 1/4. So like this. Okay, so specifically, we get this very nice tail bound, and we'll write it a bit differently here to also show that it's exponentially decaying in n as well. Right, so you can multiply here both sides by n, you get y minus n bigger or equal than nt, and then change from t to nt, and you would So since it's t squared here, you would either see n, so you would see n disappear from there and go in the denominator. But this is sort of the more intuitive form. Okay, so we have a proof of this, but the proof is simply applying what we have said before, that the sum of subexponentials is still subexponential, and applying the tail bound for subexponential random variable. Okay, so it turns out that also that the motivation for bounding a tail of a chi-square distribution comes from trying to approximately count the number of triangles in the graph. So I don't understand it that well myself, but it is how I learned it. So somehow, if you want to Google something in this direction, then Google estimating moments in a stream. And somehow this helps you estimate moments in a stream. Okay, that's all.